So today we're going to continue on with our OBD II system and talk about kind of why it came to be, what it's here for, and some of the ways it functions and actually turns the check engine light on and turns the check engine light off, how it set codes, and also later on in it, I don't know if we'll get to it today, is how the system actually performs some of its own self-tests uh, to actually do self-diagnostics on certain systems. So the idea of the OBD2 system, second generation, was to fix some of the inadequacies of the first. So one of the biggest problems of the OBD1 was the system was not tested for proper function. In other words, it was tested for failure. It was tested, are you broken? But it wasn't tested, are you working correctly? So in other words, if a sensor was bad, reading 5 volts on a 0 to 5 volt sensor, reading 0 volts, we could say, hey, that's bad, you're reading out of range. OBD1 would see that. What it wouldn't see is, first of all, does it make sense that the coolant temperature is saying 20 degrees, and yet the engine's been running for 15 minutes and it's 80 degrees outside? Clearly that's not plausible. So, so aside from normality, we started looking at rationality for sensors. The other thing that OBD does that was almost really not done by OBD1 with very few exceptions was test to see if a system was operating correctly. And if it wasn't operating correctly, how much had it degraded, with the goal of setting a code when the system is degraded a certain point before it has completely failed. So I'll use the Kellogg converter, for example. We set a code for a bad Kellogg converter when the efficiency normally drops below 50%. So we're not setting a code when the Kellogg converter is at 0. We're setting it when it's lost 50% of efficiency. And we see that with other systems where we're not setting it when it stops working. We're setting it when it has degraded to the point to where it's going to affect emissions or potentially affect emissions. Not that the system's completely failed. So that could be a passage plugging up. It could be like a vacuum. There's a lot of different things that can cause a system to degrade. But OBD1 basically didn't do that, with very few exceptions. So this was a big thing. And so we wanted to be able to test these systems under normal operating conditions. So under load, when they're working, how well are they working? Not just, are my sensors okay? Am I hooked up electrically? So OBD1 mode monitoring, degraded emission systems did not set a check engine light. Got it. And so degraded systems did not set a check engine light. The fuel evaporation, catalytic converter, and air injection systems were not monitored also. These are 3 emission control systems that were not checked to see if they're functioning or not. O2 sensor was not monitored by most manufacturers. So the oxygen sensor was really not monitored to see if it was working correctly, just to see if it wasn't dead. The EGR system was not monitored by most manufacturers. California Toyotas did check it. They used a temperature sensor, and California Mercedes used the oxygen sensor to test the EGR. Other than that, pretty much no one else tested it. So, I mean, it was really the exception. Misfires were not detected. So if an engine was a 6-cylinder engine and only running on 5 cylinders, we didn't notice that. It didn't turn the check engine light on, didn't set a code, and so on. Shifted air refuel ratios were not monitored, with few exceptions. So if the car was running excessively lean or excessively rich, again, it would not set a code, with few exceptions. NOx emissions were not monitored, and you could argue that they're not monitored still. When we look at catalytic converters, I'll talk about and explain really why we don't monitor on gasoline engines. We don't need to, for the most part. We do monitor them on diesel engines, on some diesel engines. So OBD2 strategies were implemented for all 1996 light duty models, both California and federal vehicles. Phase-in began between 1994 and 1996. So there are some 1994 and 1995 OBD2 vehicles. Toyota Previa, when it came out, it was an OBD2 vehicle in 94. So we do have some of these vehicles that we call them transitional. You'll see some General Motors vehicles, 94, 95, that were kind of OBD2 vehicles. Didn't follow the rules later. They were in that experimentation, implementation phase, and several manufacturers did that. The OEMs, original equipment manufacturers, were allowed to double EEPROM flash to lock out problems affecting CSI. So I just gave you alphabet soup here. So let me break it down. OEM, original equipment manufacturer, that is who makes the vehicle. A double EEPROM is electronically erasable, programmable, read-only memory. So when we first started putting computers in cars, they had ROM, read-only memory. And if I needed to change the read-only memory, I needed to change the computer. GM came out with a PROM, programmable read-only memory, where you could replace just the PROM chip on the computer board. Then we came out with erasable PROM chips, where if you had the right tool and ultraviolet light, you could erase the PROM and reprogram. Now we have electronically erasable PROMs. That allows me to use software to reprogram a computer on the vehicle without taking anything apart, because it's electronically erasable read-only memory. So the OEMs are allowed to do updated calibrations to lock out problems affecting CSI, customer satisfaction index. So if we're doing something, maybe we're testing our EGR valve, but the customer complaint is the vehicle surges at idle and surges at cruise or going down the highway. And we're getting a lot of complaints on that because that's when we're testing our EGR. So we might change our EGR testing strategy or stop testing it altogether. And that can be approved by the federal government based on customer complaints on how the vehicle drives. Federal medium duty trucks were not required to be OBD2 until 2007. So medium duty for this purpose is defined as any truck with a gross vehicle weight rating over 8,500 pounds. And keep in mind, OBD2 regulations only go up to 14,000 pounds. So no vehicle with a gross vehicle weight rating over 14,000 pounds can be OBD2, because the regulations only go to 14,000 pounds. So at 14,000 at 1 pound,
porque no está
it's not
contestando.
OBD2.
Ya le hablaron.
Keep in mind that these vehicles, 96 and newer, whether they're OBD2 certified or not, will still have that 16-pin diagnostic link connector. And that's why I make the distinction that that's a 16-pin diagnostic link connector and not an OBD2 connector, because there's plenty of vehicles that are not OBD2 certified that have that 16-pin diagnostic link connector. So one is the connector that we're going to hook the scan tool up to talk to it. The other is the programming and the rules that the computer system on the vehicle has to follow. Two different things. So check with manufacturer regarding configuration if you have a question. So the first place I would want to look would be my underhood emission label, because that'll tell me if a vehicle is OBD2 certified. So who controlled OBD2? Well, California Air Resources Board did from 94 to 98. Remember, OBD1 is a California certification. So it made sense that OBD2 would be a California certification. And what we found is a lot of very poor compliance from vehicle manufacturers in 96 and 97 and into 98. So in 98, the EPA took over. So EPA controls OBD2 to this day. And we see when we look at technology, when we look at different systems, there's a lot of OBD2 vehicles are very different after 2000 than they were before 2000 because the EPA came in, set a bunch of rules and said you have until 2000 model year to fix these issues. So we have a lot of issues with early OBD2 vehicles. Keep in mind, even though a 2021 vehicle is an OBD2 vehicle, that OBD2 system is very different than an OBD2 system I'm going to find on a 2008 or a 2000 or a 1996, because OBD2 has evolved through legislation and regulation over the years. So things that are tested now are required to be tested and set codes on a 2020 vehicle. Data that I can get on a 2020 vehicle might not be available on a 2010 vehicle or a 2014 vehicle or a 2008 vehicle or so on. So even though the framework that I'm going to look at is the same, my ability to get certain data or the requirement of manufacturers to set certain codes changes by year when those regulations came into effect, even though we call it all OBD2. So OBD2 has continued to evolve and change on what it does, what it's looking at, how finely it's looking at things. So there's things that we look at today that we didn't look at 10 years ago.
Do you use different scan tools for the different years?
No, that is one of the great things about OBD2 is we're required to have backwards compatibility. In other words, I'm required to be able to access all of these vehicles using the same menu structure. So the menu structure is basically the same. We have some new things that are available on newer vehicles than we had on older ones within that structure. So if I'm using a really old tool, it might not access certain modes of operation.
Okay.
But I'm able to use the same tool. The difference that we had for a while was pre-CAN vehicles versus post-CAN vehicles, and a lot of early scan tools couldn't talk to a CAN vehicle. Today, all generic scan tools are able to talk to CAN and pre-CAN vehicles, so it's a non-issue. So a lot of it is more software driven on the tool as far as some of the modes. For example, mode 0A wasn't supported prior to 2010. So if I was using a scan tool from prior to 2010 or maybe even 2011, 2012, I might not be able to access that mode. But almost every vehicle, 99.8% of vehicles made, use that mode since 2012. So therefore, any tool probably made after that is going to support that mode. I'm going to be able to access that information on a full scan tool. And that's where you get into a code reader versus a full scan tool, because a code reader might not support all the modes. And I have a video that I just put up on the as a lab, and I go through all the 10 modes of OBD2 and talk about them a little bit and kind of show you how to navigate. So Society of Automotive Engineers, SAE, sets the standards. So as they set requirements for common systems, programming changes. So SAE in this country sets the standards. They work in conjunction with ISO in Europe. So ISO sets the European standards. So a lot of times we'll see stuff SAE/ISO because that would mean it's a shared standard. So who first set the standards for OBD2? CARB, absolutely, number one. So terminology and vocabulary, OBD1 versus OBD2. So vernacular standardization or newspeak was developed, which created a standardization of terms, which was great because before this, everyone had their own little name for everything. So if you're trying to order a part or trying to look up information, you had to know what that manufacturer called it or you couldn't find the information. So General Motors used to call their diagnostic link connector an ALDL. Well, now universally, regardless of manufacturer, it's called a DLC. Ego, Ford used to call it an ego sensor. Some other manufacturers also use that, say for exhaust gas oxygen. Now by law, it has to either be an O2S or an HO2S. We also see some AFS and HAFS fuel sensors, but we standardized. We used to have a mat on a car, not the one that goes under your feet. This was the manifold air temperature sensor. Well, now universally, we have to call it an intake air temp sensor. So again, you can see where it used to be very complicated to work on different manufacturers' vehicles because you had to know the vernacular that that manufacturer used to look up stuff in the component locator, wiring diagrams, and so on, where now it's standardized. Integrator and block learn are now short-term and long-term fuel trim. So those are our manipulated values for fuel trim. So we also had other things like adaptive and multiplicative. I mean, we had all kinds of different, names to describe that short-term and long-term strategy. OBD2 said, no, this is what you have to use. This is what you have to show the technician on an OBD2 scan tool. You have to give it to them in the same scale, same terms, regardless of which vehicle. So you can see why, 25 years ago, many people didn't work on European cars. A lot of people might not work on Asian cars, or if they worked on Asian cars, they might not work on domestic cars because they were very, very different in vernacular and in strategy. What OBD2 did is it really allowed people to access and work on a much greater variety of cars. And where it used to be, again, European was a niche thing. Now with OBD2, when it comes to the engine management system, anyone can plug in and get codes and try to do diagnosis on those cars. That doesn't necessarily mean they're good at it, but because it all looks the same, people are much more willing to try it. We also had ESS, which is now the CKP for crank sensor. So that was our engine speed sensor. So you can see where, these other acronyms kind of make sense, but you can see we're having a standardized CKP, whether I'm working on a Mercedes or a Hyundai, would be helpful if I'm trying to diagnose the car. So a CKP code's a CKP code. I know it's going to be on the crank sensor. I know that, I know what it is because it's the same term every time. I'm not having to go spend 10 minutes, look up what the heck is this? And then after 10 minutes, you find, oh, it's that, which used to be very common. And it was 10 minutes if you're lucky, because there was a time when we didn't have computerized information systems. Everything was in books, and you were limited to what you had in the book. And it was pretty good. I mean, each year for domestic vehicles, up through the 80s, up until the late 80s, we got a book about this thick, which covered everything for every domestic vehicle. In the late 80s, we got a book about this thick for Ford, Chrysler, and Jeep, and one about this thick for GM. GM gave a lot more information. Then eventually, by the mid-90s, you got up to 3 volumes for domestic and 2 volumes for import. But you used to get everything for import vehicles that year, about this wide. That's it. Everything from Alfa Romeo to Volvo, right here. Pages were pretty thin. So the amount of information that was available was pretty limited. And the early 90s, a company came out that revolutionized this. It was called AllData. And at that time, they had 8 million pages of information accessible on their computer system. And it was on CDs, and you had to change the disk for which system you wanted to look at. And it got to the point before they went online. I think we were like at 60 or 70 disks, and those disks would come out every quarter. And you had a subscription, and they'd send you disks. And boy, that was before it went online. Very, big change on the amount of information we can get. So OBD2 commonalities, standardization facilitated by SAE. SAE was comprised of reps from the original equipment manufacturers. OBD2 guidelines were established by SAE and ISO. OEMs interpreted guidelines differently. So OBD2 is the same but different. So, for example, the self-test is required. Some self-tests are required to test a system twice before setting a code to make sure that there's actually a problem there. Mitsubishi and said twice, well, that's, kind of a minimum standard. We want to really make sure that this system has problems, so we're going to test it 5 times. So as a consequence of that, early OBD2 Mitsubishis would not set their self-test monitor or their OBD2 monitor because it would never get to that 5 times. So it wasn't a deliberate to get around the rules. It was, again, misinterpretation. If I say something in this room and we're all speaking English in this room, we're still going to have misunderstandings. So now let me take something from this room, send it halfway across the world, and have it translated to another language and see how many misunderstandings we have. So, you can see where things are interpreted differently. Things tend to be interpreted differently also by region. So Asian manufacturers do things different than European manufacturers, which do things different than domestic manufacturers. And I think a lot of that comes from the school of thought. So whether it's engineer worked for Volkswagen and now they're working for Mercedes, or whether they all went to the same engineering schools. I know in domestic, engineers will work for GM, Ford, and Chrysler. They'll move around during their careers, not uncommon. And I can believe the same thing happens in Asia, where it's either an educational thing or they're actually sharing stuff after people are in and they change companies. But there is definitely different schools of thought. So when I'm working on a vehicle and I'm doing diagnosis, I will keep in mind whether I'm working on an Asian vehicle, a domestic vehicle, or a European vehicle, because they do see things differently and they have certain traits that they do consistently that no one else does. And that can be helpful. So they are the same but different. So for example, the Germans tend to be very literal with things. And in 2010, actually, 2010, we introduced permanent codes. And these are codes that you can't clear with a scan tool. They don't turn the check engine light on, but you can't turn with a scan tool. And they're designed for once the car is fixed, the car recognizes it's fixed, and then it'll clear the permanent code. So it's a tattletale. It's all about emissions enforcement. It's a tattletale. BMW took that to permanent to mean it never goes away. So the design is for it to go away once the car is fixed and the computer recognizes it's fixed. On early BMWs, it never goes away because permanent means permanent in German, apparently. So it's there, it never goes away. So you have these different interpretations that different manufacturers have. So we have the same regulations, and a lot of times these differences in interpretation are there until they create a problem. And then it's kind of like, that's not what we meant. You need to fix this. But there's usually a couple model years where we have these kind of weird anomalies. And that's very common as we go through and evolve. There are 10 modes currently used in OBD II. So OBD II use common terms for sensors and other components. Is that true or false?
True.
Okay. So let's look at our 10 modes. So standardized OBD II modes allow generic scan tools to access the same subset of information from all cars. So these modes are kind of like stories in a building. So these modes are defined. Not all vehicles use all modes. But this is the framework. So we're always going to find the same information in the same mode, regardless of manufacturer. And what I mean by same information is the same type of information, not necessarily the same specific information, because one manufacturer may support a test or a sensor that another one doesn't. So for example, not every car has air injection, or not every car has an EGR valve, and so on. So mode 1 is my current parameter data, or PID. Parameter identification data is what PID stands for. And your scan tool is basically an address book. And everything in OBD II is done in what's called hexadecimal. So hexadecimal is a scientific numbering system based on 16. And that's what the dollar sign in front of that mode 1, mode 2, mode 3 means, is that it's a hexadecimal number. So it's a 0 and a 1, or it's a 0 and a 5. So like I said, the hexadecimal system is a 16-digit numbering system. And we did this because back when OBD II was first being implemented in the early 90s, computing power was very expensive. I remember at this time, I think it was $45 a megabyte for computer memory for RAM. And that was a fixed cost. It was 45 bucks a megabyte. You look at the computers today, they have gigabytes of RAM. So memory was very, very expensive. Well, inside a computer, we have bits and bytes. And in a 4-digit system, which is 4 bits, half a byte, you have 9,999 possibilities, basically. By going to hexadecimal, I now have 65,535 possibilities in those same 4 digits. So without increasing the memory, we have increased the ability to communicate data 6.5 times. Now, remember what I said about backwards compatibility, right? Memory's cheap now. The problem is that backwards compatibility, we're still built on the same OBD II frame. So it's like buying a house that's completely remodeled and you find out that the basement was installed during the Revolutionary War. Okay, so yeah, some of the plumbing, some of the other things, there's still going to be some idiosyncrasies here. Yeah, those are boulders they use for the basement. That's not concrete. So that's our OBD II system. We're still built on this foundation of technology from the early 90s to allow for this backwards compatibility. So some of the things we do in OBD II are still based on this, including our hexadecimal system. So my mode 1 has my current parameter data. My first PID is my monitor status and check engine light status. So it's going to tell me which of my monitors are complete or not complete, and if my check engine light's on or off. Mode 2 is or 02 is my freeze frame data. So when we set a code and turn a check engine light on, we capture certain pieces of data and save it there for the technician to go and look at to understand what was happening when the failure happened. And we're going to look at each of these modes in a little more detail. Mode 3 is confirmed diagnostic trouble codes. These are diagnostic trouble codes that may or were recently commanding the check engine light on or the mill on. So in order for the mill to be turned on a OBD II vehicle, there has to be an emission code capable of turning the mill on stored in mode 3. So keep in mind, we have 2 parts of our computer system on the car. We have the OBD II generic side, and we have the manufacturer side, which we call the enhanced side. Both sides can set codes. Both sides have data. Both sides do different things. So it's kind of like, again, going way back, my first computer was a DOS computer, disk operating system. I had a program that I bought for it called Windows 3.1. And you could click on that and it would open up Windows. So you could run Windows or you could operate in DOS. And certain things were much easier to do in DOS. Other things, because Windows recognized what a mouse was, certain things were easier to do in Windows. I really liked DOS. DOS was great. It was fast. It was efficient. And I could type. So it actually made me a better typist. But I was able to navigate and use DOS. And DOS used a lot less memory. There are some advantages to it. But we had 2 operating systems on the same computer. And they looked very different. DOS looks very different than Windows does. You buy a new computer with Windows, you get pretty pictures, you get sound, you get all these icons, you get all this stuff and this pretty screen. And Windows 10, of course, you get scenes of wherever. On a DOS computer, you get C:\\/ flashing at you, and you just spent $3,000 for something that turns on and says C:\\, and you're like, what do I do now? Very, very different experience, very, very different system. Our computers on our cars have both systems. They have this really nuts and bolts generic system that's heavily regulated and has to conform to very strict rules. And then you have the manufacturer's side that doesn't have to follow those rules the same way. They can do different things. One thing they cannot do is turn the check engine light on. In order for the check engine light to be turned on, the code has to be in mode 3. Only the OBD II system can turn that malfunction indicator light on. So I can have codes in the enhanced side of my computer system, and we see this a lot on European vehicles. But we don't have any codes on the generic side, and the light's not on, right? Because some codes are considered emissions codes and other codes are not. And this is up to whatever the manufacturer is willing to lie to. So it gets a little more involved now, but that's kind of in a nutshell. So the advantage of OBD II is I can go to any car and leverage how OBD II has to work. And there's times I'll diagnose a car using OBD II, even when I have a factory scan tool, but the factory scan tool is no help. There's other times, because of the limits of OBD II, I need that enhanced scan tool capability. And that may be an aftermarket scan tool, or it may be a factory scan tool, depending on which capability I need and what's supported by the aftermarket tool. So mode 04 is how we clear diagnostic trouble codes and reset emission-related diagnostic information using a scan tool. So when I tell it to clear codes, this is how it goes in and clears codes. Mode 05 is oxygen sensor monitoring test results for pre-CAN vehicles. So this mode is not supported after 2008. And it wasn't supported on any CAN vehicles prior to 2008. And not all manufacturers used this mode. And this mode is almost entirely useless for diagnosing vehicles. And I've looked at thousands of sets. I have fixed probably 5 or 6 cars with it, but I probably looked at a couple thousand cars to do that. Oops. So mode 6. Mode 6 is the test results for my non-continuously monitored system. So I have 2 types of systems that are monitored. One is continuously monitoring for opens and shorts. Am I electrically connected? So we have many circuits and many systems that are continuously monitored for opens or shorts. I'm kind of continuously monitoring for misfires, and I'm continuously monitoring if my fuel control system's not working correctly. We have other systems that are only monitored under a specific set of conditions. In other words, I only want to run a test on the catalytic converter when conditions are correct for the catalytic converter to perform properly. I only want to run a test on the EGR system when conditions are correct for the EGR system to perform properly. And so those are what we call non-continuous monitors. So results of the tests for those non-continuous monitors are stored in mode 6. So if I have a code, means I had a failure, I can go into mode 6 potentially, if it is a supported test, and see exactly how bad did I fail. Did I fail by 1 point, or did I fail by a lot of points? Is the system barely out of specifications, or is it dead? And this can do a couple things. It can help me develop a diagnostic plan, excuse me. It can also help me verify that I've repaired the vehicle. Because if I do a repair, go run the self-test again, look at the new results, I can see that the new results are much better than the old results, and yes, I did fix the vehicle. Mode 7 is where we put our pending codes. Also can be described as tests that failed their last trip. In other words, the last time we tested this circuit, it failed, or this system, it failed. Codes in mode 7 will not turn the check engine light on. So these are pending codes. We've found a problem, but we're not sure if it's a consistent problem or an anomaly. So on OBD1, the check engine light would come on anytime the computer thinks it saw a problem and go out anytime it thought it was okay. With OBD2, now I can get a code in mode 7 anytime it thinks there's a problem. But if the next trip passes, it goes away. So I may have a code that's intermittently coming in and out of mode 7, but it's not going to turn the check engine light on because it has to mature and get to mode 3 for that. And I'm going to break down that process for you. Mode 8 is bidirectional controls, which would allow a scan tool to command functions on a vehicle. This was never required or implemented for generic OBD2. There are, from what I understand, a few vehicles out there that will support some of the bidirectional tests in OBD2, such as closing a purge solenoid or things like that. I have never had a vehicle do that. I have had techs send me, I've had 2 techs, to be specific, send me specific examples of how it worked on them. One was on a Ford F-150, one was on a Lexus. And that's 2 examples out of, probably 800 students that I had when I taught that class that got back to me and said, no, I actually got it to work. Here's the example. Here's what it was, and gave me information. So I've never had it work. So I stopped trying. If I want bidirectional controls, I need to go to the enhanced side or manufacturer side. Mode 9 is my vehicle data. So this is different than my live data. My live data is what's happening on the vehicle now. Mode 09 is my program data, my VIN, my calibration. IPT stands for in-use performance tracking. So that's one of the algorithms that we use to determine if the vehicle is performing self-diagnostics at a reasonable consistency. Then we have mode 0A. These are our permanent emission related DTCs. These were implemented on half the vehicles sold in 2010 and about 99.8% of the vehicles sold in 2012. So there's a phase-in period there. It is stored whenever the mill is commanded on. So when a code goes to mode 3 and turns the check engine light on, that code will be stored in mode 0A. When I erase the codes using a scan tool, it will not be erased from mode 0A. It's only erased by the OBD2 system itself once the PCM has confirmed proper operation. So even disconnecting the battery will not erase codes from mode 0A. The only way I can get rid of codes from mode 0A is either the car is happy and it says, I'm fixed, I'm getting rid of this code, or reflashing or reprogramming the powertrain control module. That's it. So OBD2 requirements must be installed on all light-duty vehicles, 1996 and newer. Must be able to determine the operating condition of the vehicle's emission control system or emission control strategy. So we're no longer looking at, is it bad or is it broken? We're looking at, is it functioning correctly?
All those models coexist on the system, right? Model 1 through Model 9.
All the modes what, Luke?
Coexist in one vehicle.
All the modes exist in one vehicle, correct. So most vehicles will not support all the modes. So for example, if it's new enough to have mode 0A, it can't have mode 05. Because mode 05 was only used on pre-can vehicles and mode 0A didn't come out till 2010. So, but you will see mode 01, 2, 3, 4, 6, 7, 9, 10 is what I would expect to see on a modern, or 9, 0A is what I would expect to see on a modern vehicle. Looks like you're muted, Luke. Okay. So diagnostics and functions must be standardized. So this is a little misleading. There's a lot of ways to get to the same place. I mean, I bet you if you left your house and where you're going to the store, there's more than one way to get there. Some are more efficient than others. Oftentimes there's two places that it's 6 to 1, half dozen the other. I can make a left and go around this way or make a right and go around this way. It's about the same time. It's about whether I want to make left turns, right turns, deal with a certain signal, any of those things. So again, we're back to the same but different. So diagnostics are similar, but not the same. Functions the same way are going to be similar, but not necessarily the same. But when it comes to actually how the modes work, that is standardized. So the modes themselves are standardized. The rules that they have to apply to are standardized. When I get out of OBD2 and get into the enhanced side or the manufacturer side of the computer system, all bets are off. They can do a lot of things they're not allowed to do here. So in what mode is the monitor information stored? Does anyone remember? What was that, Cynthia?
Is it in 2?
No, number 3 is mode 3, which is codes. That'll be codes that turn the check engine light on.
Oh, I thought it's the P screen where you have the storage, bigger storage. Okay.
So it would be mode 1, which is my current data. So if I want to know the current status of my monitors, I would need to go to current data, which is mode 01. Now, many scan tools give you a separate menu item for the monitor status. That's a function of the scan tool. Remember, your scan tool is an address book. So it's a function of the scan tool that it's going in and pulling that data from mode 1 and displaying it to you as a separate or standalone feature of the tool. That's a function of the tool. That's not a function of OBD2. So OBD2 requirements, the system must test emission control systems, record results, and display those results. That's our mode 6. That's why mode 6 is there. We don't get that on the manufacturer side. The manufacturers aren't required to do that. They don't do that. That's all done through mode 6. A mill is now mandatory. Must illuminate when a fault is detected and confirmed. Must remain illuminated until the fault is corrected. 3 passing consecutive tests. So in other words, the check engine light is going to come on most systems after it fails a minimum of twice. That's what they mean by confirmed. And then it can't go out until the system is tested 3 times and passes 3 times in a row. So this got rid of the problem we had with OBD1, where the light's on, the light's off, the light's on, the light's off. So at this point, if the light's on, there's a fault that is diagnosable. And yet, if the customer fixes the car themselves, for example, the light comes on and they go, you know what, let me check the gas cap, and you go open the gas door and there's no gas cap there. You go, okay, let me go get a gas cap, and I'm going to put the gas cap on. It'll take 3 times of testing that fuel evaporation system for integrity before that light's going to go out. And it may take 2 weeks to test it 3 times, depending on how much gas is in it, depending on temperature, altitude, all kinds of other issues. By the same token, if it takes 2 times for it to set the fault, someone may go to XYZ Auto Parts, have the light turned off, and it takes a week and a half for it to test that system twice before it can turn the light back on and set the code. So many times customers think that's an intermittent problem. There's nothing intermittent about it at all. It just took a week and a half before it could test it a couple times. Can only be a check engine light, service engine soon, or amber picture of an engine. The generic scan tool, standardized 16-pin DLC, J1850 ISO 9140 protocol. Now we use CAN. Must monitor all OBD2 information. Now all has changed because all in 96 is very different than all in 2000, all in 2004, all in 2008, all in 2012, all in 2016. All has evolved, okay? Monitoring and DCC clearing procedures must meet CARB EPA standards and be standardized. Must display data. So prior to OBD2, most Asian vehicles did not support any way of looking at engine data with a diagnostic device or a scan tool. It didn't exist. You couldn't do it. So old school, you had to kind of figure out what you thought might be wrong. Maybe you had one of the 10 codes it supported and you're underneath the hood with a meter, lab scope, whatever, thinking about what could be in testing things because you had no way of getting that data. Freeze frame data is required. PCM parameters and test results are also required to be displayed, which is our mode 6. Continuous monitors. Input normality and rationality. Output circuits performance electrically only. In other words, if I'm looking at a sensor, I'm looking at, is it following the 90-10 rule? I shouldn't be below 10%. I shouldn't be above 90%. So I should never see 0 volts or 5 volts on a 5-volt sensor. If I do, then it's out of normality. On the other hand, I've had a car that's been turned off for 12 hours and it's 60 degrees outside. And my engine coolant temperature says it's 100 and my air temperature says it's 50. That's not rational. This car hasn't been started in 12 hours. They should be much closer to each other. We also look at the position of my throttle compared to how much air is coming through the mass airflow sensor and my engine RPM. And there's a triangle there where these numbers have to match. And if they don't match, the computer's going to set a code, which may just be a code saying, look, one of these guys is lying to me because this, and this doesn't add up. Or they might just set a code for something like a mass airflow sensor because that's how the engineers wrote the program. But it's not that the mass airflow sensor is bad. It's that the amount of air it's reading doesn't agree with the RPM and throttle position. So it's a logic code. So we start really seeing the introduction of some logic codes here on a rudimentary level in our continuous monitor. We have much higher level logic codes when we get into our non-continuous monitors. Our output devices, we're only looking for electrical performance. So we know if I am controlling the ground side of a solenoid, when my transistor is open, there should be power coming from my power supply through the windings of the solenoid all the way up to my computer, waiting for me to ground it and collapse the circuit. So is it safe to say if I don't see power at that transistor before I ground it, that I have a problem with that circuit? Right? Because I'm not seeing that voltage potential there. So therefore, that would be a open circuit. I can set a code for that. Other hand, if I ground it and I still have power there, that would also be a problem. That would be sign what? The transistor inside my computer is bad. So by monitoring the voltage on that output line, now I can set codes for high or low voltage on that signal wire based on the condition of the circuit as controlled by the computer. So it's a simple way of saying, are the solenoids still hooked up? So again, we're not testing if the solenoid works. We're not testing if it performs what it's supposed to do or anything else. All we're saying is, hey, do I have voltage potential here because I have power going through the windings of the solenoids coming up to the end of an open circuit so I can see that voltage potential. And that's what they're doing inside the computer. And that way they know if something's unplugged. Did we do that in 96? No. Did we do that in 2022, 2021? Yes. So things have evolved. Non-continuous monitors, these are computer controlled system tests. In other words, I'm going to turn something on and see if I get the correct reaction. So the scan two tools in one, we have a generic scan tool and a manufacturer specific scan tool to create a blended scan tool, which is an OBD II generic with manufacturer specific capabilities. So that is your Autel, that's your Snap-on, that's, there's quite a few tool manufacturers that make what we call a blended scan tool. It allows me to do those generic functions as well as a lot of OE or factory functions or enhanced functions. Many factory scan tools will not do any generic functions. A true generic scan tool won't do any enhanced functions. So what we really want is a tool that's a combination of both of those things. So how many consecutive trips does it take for the PCM to turn off the mill?
3.
Not 2.
3 trips.
3. It's 2 to turn it on in most cases, 3 to turn it off. And that's why I say we don't have intermittent problems in OBD II. If the light's on and it's not turning off, that means it hasn't passed the test 3 times in a row. So if it's not passing the test 3 times in a row, we should be able to test the system and find the problem. So generic scan tools, wills, read PIDs, so read data, read readiness status, that's whether our monitors are complete or not, that's what we care about for smog. Diagnostic trouble codes, freeze frame data, connect to any OBD II vehicle. What they won't do is be as fast as a specific or hybrid scan tool, diagnose the vehicle for you, or fix the vehicle for you. Keep in mind, a code is not a diagnosis. This is just a tool like a screwdriver, a hammer, or a wrench. Unfortunately, the tool doesn't make you smarter. I wish it did. I've tried. I keep buying more expensive ones thinking I want to get smarter, and it hasn't worked yet. So common diagnostic connector, which is our DLC, 16 pins total, 7 are regulated. 7 are regulated by SAE. 9 of them are whatever the manufacturer wants to use them for. Pin 16 is always battery power for the scan tool. That is something I expect you to know. The DLC is located on the driver's side near the steering column or has a label. So in early OBD II vehicles, the diagnostic link connector could be anywhere from the driver's side to the middle of the passenger side. When EPA took over, they told manufacturers that in 2000, all of the diagnostic link connectors need to be on the driver's side. No more center console, no more passenger side. What they did say is that if you have not redesigned your vehicle, we're going to allow you to leave that diagnostic link connector where it is now until you redesign that model, but you're going to have to put a label on the bottom of the steering column telling technicians where the connector is. So Volvo had it under the armrest in their center console on their S70 up until 2005 when they did the redesign. That's why it was there so late. Acura TLs had it under the ashtray up through 2001 when they redesigned the car. So that's why you see some of them on the dash or under the ashtray or these other places. That's how they were able to get away with it after 2000. Today, they further shortened it to where you need to be within 7 inches of the steering column. The DLC has to be. So they've really brought it. So they had a big wide area and they've really brought it in to where you're allowed to have that diagnostic link connector. So here is our diagnostic link connector. So here's pin 1, and here's pin 16. So I have 1, 2, 2 and 10 are controlled by SAE. Those are communication pins. 3, 4, and 5 are both ground. 6, 7 is a regulated pin. That's a communication pin. 8 is open. 9, there's 10, 11, 12, 13, 14, 15, 16. So we do have, so that is how they're configured. And here's what they are. So pin 1 is discretionary. So many manufacturers don't use pin 1. Pin 2 is a J1850 protocol. A lot of domestic manufacturers use J1850. Import manufacturers didn't. So it's not uncommon to see that pin empty. Pin 3 is discretionary. Pin 4 is chassis ground, and pin 5 is sensor ground. Pin 6 is for our CAN system high. Pin 7 is a communication pin for ISO 9141. That is your European vehicles. Also KWP 2000, which is a lot of your Asian vehicles. So Asian and European vehicles used pin 7 back in the day, or domestics used pins 2 or pins 2 and 10. Now everyone uses pin 6 and 14 for CAN. So since 2008, 6 and 14 is our communication protocol. Pin 8 is up to the manufacturer. Pin 9, again, up to the manufacturer. 10, as I discussed, that's the second half of our J1850, so Ford used that. 11 and 12 are discretionary. 13 is discretionary. 14 is low CAN. 15 was optional to go with the ISO 9141 protocol. Some manufacturers used a 2-wire system. And pin 16 is battery power. So the only ones on here that I expect you to remember is 4 and 5. That is my chassis ground and sensor ground, and pin 16, which is battery power. Those are the only 3 I expect you to know. The other stuff is nice to know. I know it because I teach it a lot, and I've worked on a lot of these cars for a long time, and there was money in knowing that. But for the class, I'm really only looking to know that. And one reason why pin 16 is so important is most of the time, if your scan tool will not communicate with the vehicle, it's because the fuse that feeds power to pin 16 is blown. Early vehicles use the cigarette lighter fuse. You know, that's the thing that no one smokes, but they have this tree that goes in there with all these things plugged into it. Or where the kid put the penny in the bottom of it and shorted out the positive and negative and blew the fuse. And if you don't smoke, you don't know the fuse is blown. So then someone goes and tries to communicate with the vehicle and they can't get any communication. It's frustrating. What's wrong with the scan tool? If your scan tool is not talking, the first thing we should be doing is verifying we have power at pin 16. This also may be the pin that's used to power up the scan tool. So if you plug a scan tool in and it doesn't power up, again, look for power at pin 16. Later vehicles might have a dedicated fuse just for that. A lot of vehicles used it for the accessory fuse, radio fuse, cigarette lighter fuse, things like that. So we've seen it lumped in with a lot of stuff, but I do see that fairly frequently. It's the first thing I check anytime I have a communication problem is to verify I have power and ground at the DLC before I start looking for other issues. And certainly over half the time, the fuse fixes it. I mean, well over half the time. Which is why I want you to know that. So which pin of the 16-pin DLC should always have system voltage present all the time? Number 4, pin 16. You notice what I said, should have system voltage present all the time. So that's why if your key is in your pocket, you're still supposed to have power at pin 16. So that is unswitched battery power. So no communication problems can sometimes be diagnosed at the DLC. must have B plus at pin 16 and grounds at pin 4 and 5. Also, your connector on your tool, if you look at the pins on it, and it has the 16 pins, 2 of them are supposed to be longer. The 2 longer pins are for 4 and 5. And that actually came from BMW out of the SAE stuff, because they wanted ground connected first before all the other pins were connected, and they wanted ground disconnected last after all the other pins were disconnected. So if you look at a connector and those 2 pins aren't longer, the connector on the tool doesn't meet the SAE standard. And where that creates an issue is not that it won't connect and work, but if it's not meeting that standard, a lot of times the pins are also thicker and they'll spread the terminals on the DLC. So when you hook up an actual certified tool that's actually made to the correct specifications, it won't read because of pin spread and you have a bad electrical connection. So something to look at if you're looking at tools. So OBD II training course, check engine light operation, and OBD II trouble code descriptions. So the mill will illuminate when emissions are equal to 1.5 times the FTP is inferred. Okay, so more alphabet soup. FTP stands for Federal Test Procedure. So that is what we commonly call a bag test. So they put a vehicle in a room, run it through a specific set of operating conditions, and measure the total emissions produced by the vehicle in the room, not just out the tailpipe, total emissions. And they have to meet the federal test procedure for that year in vehicle classification. They have to put out less emissions than that. And to give you an idea how tight that is, if it takes a car a second to start, longer than it's supposed to take, the vehicle will fail. I mean, they are very, very tight now. So since I'm not measuring the gases coming out the tailpipe going down the road, we're going to infer that the car would be polluting based on the type of failure. So if we infer that based on the fact the catalytic converter is not working correctly, we can infer that emissions would be higher out the tailpipe. Therefore, we're going to turn the check engine light on. Since the thermostat is not working correctly, I can infer that that would affect fuel control and cause me to potentially pollute. So therefore, I'm going to turn the check engine light on. This is the only time that we are legally allowed to turn the check engine light on. So if I have a misfire, if I'm running on 3 cylinders instead of 4, that would what? Cause my emissions to exceed 1.5 times the federal test procedure in theory. So manufacturers get in a lot of trouble if when they bring a car back in for EPA testing after the car's been on the road for a while, and the vehicle fails the federal test procedure by more than 1.5 times, and the check engine light's not on. So do you think they're going to probably turn that on before it hits 1.5 times? Oh, absolutely. So they are, as much as they don't want the light on, because that means warranty repairs and customers get unhappy, they don't want to go the other way where they're going to get their hand slapped really hard either. So catalyst damaging misfires is one of the big issues we have. And that is why the check engine light, instead of being on, will start flashing. If the check engine light is flashing, you should not drive the vehicle. Now, that being said, sometimes if you put your foot in it, it's flashing. If you let your foot off, it'll stop flashing and go back to solid. If you can get it back to solid, then you can baby it to wherever you need to go. But if it's just flashing all the time, you should not drive the vehicle, because a catalytic converter can melt down in a very short period of time. I'm talking a mile, 2 miles. They say damage can happen in as little as 12 seconds. So, I have a catalytic converter that melted out. I just ran across a piece of it. It made it 20 miles from brand new to complete meltdown and plug in the exhaust, 20 miles with a misfire. I was pretty proud of that until I talked to another instructor. He had one that did it in 8 miles from cat install to meltdown. Catalyst damage happens a lot earlier than what it takes to melt down the ceramic substrate of the cat. You got to be over 4,000 degrees to hit meltdown of the ceramic. So, I mean, you're talking extreme heat. We start doing damage to catalytic converters at 1,462 degrees. That's when we start melting the first element in the catalytic converter that causes it not to work. So I'm over 4,000 before I finally melt it down, but I'm destroying it at 1,462. So you can see where it just doesn't take long. If the PCM or the network malfunctions, it can also turn the mill on, but only if it thinks that malfunction is going to cause emissions to increase. So, for example, not all network codes are going to set a check engine light because not all network problems are going to cause emissions to go up. But if I can't see how fast I'm going, that certainly could, because now I have to shift my transmission differently. I'm not going to be as efficient. That's going to lower my gas mileage, which will increase emissions. So I'm probably going to turn on if I can't talk to the ABS module. But if I can't talk to someone else, I might not kick that on. So it really comes down to what part of it is malfunctioning. So again, network problems, same with transmissions. Some transmission failures will turn the check engine light on, others will not. And people go, well, wait a minute, transmission, that's not, part of the emission systems. Well, say your transmission cannot go into overdrive. And so would that affect your gas mileage? And we measure emissions in grams per mile is how the federal government measures emissions. So if I'm getting less gas mileage, would I be putting out more grams per mile, even if my engine's running just as clean as it was before? Because I'm getting less miles out of a gallon of gas. So therefore I put out more grams per mile of emissions. That's why the light comes on. So, it kind of makes sense when you think about it, but there's a lot of bad stuff. I've had customers come in and their cars fail smog because of a transmission code and the check engine light's on, and they want to argue with me. They say, well, my mechanic says that has nothing to do with emissions. That's just the transmission and you're supposed to pass my car. Okay, well, first of all, you're going to the wrong mechanic. And second of all, he's wrong. And, let's break down why he's wrong. And no, I am supposed to fail it. And I mean, I've had customers leave mad, sure I'm wrong as they leave, going to the next place to fail again. Because they're believing the mechanic who told them what they wanted to hear, not what reality was. I mean, again, are you believing the guy that who told you one thing, or me and the state, because the state failed it, not me, that are failing your car? I mean, and I have a license, so which is probably telling the truth here, but people don't always do that. They are sure that I'm wrong because their mechanic told them. The mill shall not be used for any other purpose. So if we look, if the mill is on, a fault has been detected and confirmed, means there's something to diagnose. I should not just be turning off the check engine light and seeing what happens. Because it's going to come back on. If it's fixed, it'll turn itself off. It does that after 3 tests. So I don't need to do anything. So I should never just be clearing codes. If the mill is off, then no fault has been detected, or the test is not run, or a fault has been detected but not confirmed, so it's a pending code in mode 7, or the fault has been confirmed and has had 3 good trips, so the mill is back off. So the check engine light being off doesn't mean there's no problem. I don't know that till I interrogate the system. If the mill is flashing, a catalyst damaging misfire or air fuel problem is detected. What I can tell you is I have never seen or heard of an air fuel ratio problem causing the mill to flash. Under regulation, they're allowed to do it. I've never seen anyone do it or have heard of anyone doing it. So if the mill's flashing, it's a catalyst damage and misfire. So turning off the mill, I can clear codes through a scan tool using mode 4. I can remove power from the PCM, which may work by disconnecting the battery, disconnecting the fuse, removing the module, but it doesn't always work. Or we can have 3 consecutive trips that are completed without any further faults detected for the system that set the code. So I can have other faults. I can set other codes pending. But as long as the code that turned on the light passes for 3 trips, it'll command the light off. Now, there may be another code that's failed that now commands it on, and that can change which code's actually turning the mill on. Turning off the mill by using the scan tool or removing PCM power also clears codes and monitors. So if I use the scan tool to clear codes or I disconnect the battery, I lose all of my self-test data. So all the monitors, all the self-tests will go into incomplete. All of my test results will be erased. All my petting codes will be erased. My freeze frame data will be erased. So unfortunately, what happens is people will go to XYZ Auto Parts with a check engine light on. XYZ Auto Parts gives them a code number and then clears the memory. And then the customer brings the car into the shop and says, I want this code number diagnosed. The customer's gotten rid of all the diagnostic data that we would use to diagnose the code in many cases. So now we're faced with a situation where I got to tell the customer, we're actually going to charge you more because I have to go drive the car and get it to fail again so I can diagnose it because you got rid of all the data. It's like trying to figure out why a plane crashed when you don't have a flight recorder. It gets difficult. You can go by golly, I think, maybe, whatever, but you really need data. And not that you can't do it without it. Sometimes you can't, but not that you can't do it without it, but it's going to be far more labor intensive. How much higher than FTP standards do emissions have to be before the mill will be turned on by the PCM?
1.5.
Number 3, 1.5 times. On an OBD II vehicle, the check engine light can be turned on because an oil change is needed. True or false? False. Now, that being said, we do actually have codes that'll turn on the check engine light. Chrysler does this because someone puts the wrong oil in the car. Or if the oil is extremely old. It has to do with viscosity and their variable valve timing system, how it works. If it's a delayed response or it's not responding in the correct time frame, it sets a code for wrong oil. First time I saw that, it was like, huh, this is interesting. I haven't seen that before. That's why I say, I never like to say always or never. When someone says something, it's like, okay, let me see what you got. Because it doesn't make sense. You may be misexplaining it, you may be wrong, or I may learn something new today. You just never know. So DTC requirements. PCM must store diagnostic trouble codes for detected faults, either pending or confirmed. DTCs must stay in memory until cleared following repair or until 40 consecutive warm-up cycles. And I will get into specific what a warm-up cycle is later on in the presentation. And really, it is better to look at it as 40 consecutive trips or tests is really more accurate. If it is a misfire or fuel control problem, it takes 80 consecutive warm-up cycles or trips for severe misfire or fuel control problems. So consequently, it's not uncommon for me to go into a car and have multiple codes, because it may be something that was from months ago and has already been fixed, but never cleared, but it hasn't gotten to that 40 or 80 times yet. So we have a couple different types of codes. We have A codes. A codes are a one-trip code, meaning it sees the problem, the light comes on. So a cat damaging misfire would be a good example of a one-trip code. A mass airflow sensor or throttle position sensor that's not plugged in will be a one-trip code, right? Because it's something that, whoa, we can see this is bad and this is really bad, we're turning the light on. So consequently, when you put something together and you forget to plug in the intake air temp sensor or mass airflow sensor or DPS, you start the car and the check engine light comes on right after you start the car, you forgot to plug something in normally. And if you're like me, where you're half blind and can't find the milk in the refrigerator, I can go look underneath the hood to see what I didn't plug in, or I can just plug the scan tool in and have the computer tell me what I forgot to plug in, which is what I go with, because I can't find the milk in the refrigerator, even though it's on the door. So always good to know your limitations. Type B codes are normally two-trip codes, although some of these codes may take up to 6 times before they'll actually mature and turn the light on, unless the memory's just been reset. Then it only takes 2 times. So in other words, going down the road, we haven't had a problem in this car in 2 years, and something messes up a couple times, maybe we're not going to turn that light on. We're going to wait to see it 6 times. But oh, now you cleared the memory, and the next 2 times it fails, that light's coming right back on. So manufacturers have some strategies there, and part of that's for customer satisfaction. So this is a serious emission-related failure. Type B codes will also turn the check engine light on. So A codes and B codes will both turn the check engine light on. C and D codes will not. These are not emission related. It will not illuminate the mill. However, they may be displayed in either modes 3 or mode 7. So this is up to the manufacturer. So for example, a P0325 code, which is for a NOx sensor, will turn the check engine light on a Honda or a Chevy truck, but it will not turn it on a Nissan, because Nissan says that's not an emission-related code. Honda and GM and Toyota and many other manufacturers say it is an emission-related code, and they turn a check engine light on for it. Nissan does not. Same code number, same description. Nissan says, that's not a big enough part of our strategy, it doesn't lower emissions. Well, if they're lying, they've been doing it for over 20 years and EPA hasn't come down on them yet. So maybe they're not, maybe they don't do much with the NOx sensor, or maybe they've already detuned it. The NOx sensor doesn't have a lot of control. I have no idea. But the same code number, meaning the same thing, might be a B code for one manufacturer and a C code for another manufacturer. Remember, C and D codes can't turn on the mill. Common numbering system for all DTCs is alphanumeric, 5-digit. DTCs must be similar in meaning. That doesn't mean they mean the same thing. DTC designation must be common, but not the same. And it's standardized at J2012. So our DTC numbering, my first digit is an alpha character. And I'm going to have a P for powertrain, a C for chassis, a B for body, and a U for UART. because obviously engineers got a hold of this. If it was auto guys, it'd be an N for networking. But they used a networking term UART for these, so a U code. But U is our networking code. So this tells me what area my problem is. Is it in the powertrain? Is it in the chassis, the body, or the network? So powertrain codes are normally only set in powertrain modules. So that's going to be an engine system or a transmission system. Or if I'm on a hybrid vehicle, that could be in my battery computer or my inverter computer, right? My hybrid control computer, because that's what? Powertrain. On the other hand, chassis codes, that's going to be my ABS system, suspension system. Body codes, my radio, my climate control, airbag system, body. Anyone can set network codes because everyone's on the network. And it's also interesting because you can go into some modules where you get multiple code, not just one plus a U, but you actually get multiple code designators on some of these general electronic modules and things like that, where you might get C and B codes and U codes out of the same module because of how it's networked and what it's doing. So the second position, or thousandths position, is going to be a 0, 1, 2, or 3. So a 0 code is an SAE generic code. P0, fill in the blank. B0, fill in the blank. 1, 2, and 3 are manufacturer specific codes. So a P1 something or a P2 something or a P3 something is going to be specific to that manufacturer. Now, the name of the code is universal. Okay. So a P1495 code is always going to have the same title or name, regardless of manufacturer. Its meaning and set parameters are going to be very specific to that manufacturer. And so these are codes. And really what this came about is originally we'd only had P0 codes. And the regulations were that everyone had to have access to these P0 codes. Well, the Europeans, not liking universal access, said, hey, the regulations don't mention anything about, these higher numbers. So we're going to use these higher numbers. So that's where our two P2 and P3 codes came from. And they still use a lot of P1 codes because I don't have to give that information out because it's not generic. It's going to be proprietary. Then SAE and ISO came around and said, oh, no, you got to release it for everything. So that's why we got the 2s and the 3s. That's why we have so much. Aside from, there is a lot of code numbering and a lot of different code options. Manufacturers were trying to get sneaky and they had to kind of unwind it a little bit. But P3000 codes are very common on hybrid vehicles. We see a lot of P2000 codes on European vehicles, but we do see some on some Asian, some domestic. P1000 codes are fairly common. Domestics use a lot of P0 codes compared to European vehicles that use very few P0 codes. So it really kind of varies by manufacturer and accessibility. A good scan tool will get you into all of this. Some code readers will only read P0 codes. If you can't find information on a BMW with a P2485 code, just put in P2485 into Google and see at least what it says it is. That'll give you an area that has to be set in the code. It's not going to give you the exact code definition or what set the code, but at least you have some idea of what system you're working on at that point or what area it is. That's kind of a quick workaround. Some manufacturers don't share well. So next are 300 digit, and now I'm going to get into just powertrain control, is the system fault. So 100 is air fuel metering. 200 is also air fuel metering, but the fuel side, so injectors and fuel pump. So 100s are normally my sensors or logic. 200 is normally my injectors and fuel pump controls. 300 is going to be my misfires and ignition system. 400 is my emission control system. So everything from air injection to Cali converters to EGR to fuel evap is all in 400. 500 is vehicle speed and idle control. 600 is computer output circuits. 700 is transmission. And 800 is transmission. So again, using this logic, if I have a P2719 code, it has to be for the transmission. So there's a manufacturer specific code for a transmission because the P means powertrain, the 2 is manufacturer specific, the 7 means transmission. The last 2 digits are going to be the exact fault. So even if I don't, without doing any research, at least I know, oh, this is a transmission related problem. So, you know, having this code decipher can really help. And I'm not going to expect you guys to memorize to the 3rd digit. I do expect you guys to remember the 4 letters and also the 0, 1, 2, 3. That 0 is generic, 1, 2, and 3 is manufacturer specific for the thousands position. This other stuff I do not expect you to remember. I'm not going to test you on it. It's good to know. It's helpful to know, but I'm not going to make you know. A pending code will turn on the check engine light. True or false?
True.
False. Only mature codes in mode 3 can turn the check engine light. Pending codes are in mode 7. Mode 7 cannot turn on the check engine light. The first digit of a network code on an OBD II system is which of the following?
P.
Yep, number 3, U.
U.
Right? UART code. Like I said, engineers got a hold of this. So the first digit of a network code would be a U code for UART. Make too much sense if we had an auto speak and used N for network. So my 4th and 5th digits, my 10s and 1s designate a specific fault. So an example would be a P0301, engine cylinder 1 misfire detected. So P, powertrain, 0 generic, 300 is my ignition system, 01 is cylinder number 1. And this is telling me that cylinder number 1 has a misfire. So if I had a P0351, that would be cylinder number 1's ignition coil circuit has a circuit problem. So we can, you know, so where a P0300 code is a, hey, I just have a misfire, I'm not sure which cylinder. So these codes can either give you a general, someone's running badly, or specific, I really don't like how number 1's performing today. You need to go test it. So you see how this breaks down on the number to get down to a specific description. So once I get a description like this, misfire is detected, 2 things I need to look at. One is, how does the computer determine it's detected a misfire? The other is, what are the things that could cause it to misfire? Well, we know from the lab that I need ignition, compression, and fuel. That's what causes a misfire, is if I'm missing one of those things. So now I have a diagnostic path. So how did this system detect it? Well, it's looking at crankshaft rotation, and the crankshaft didn't speed up correctly. So what if I test the cylinder and the cylinder works great? I can't find a problem, but this code keeps coming back. Could I have a problem with the trigger wheel as it's going around? Maybe the trigger wheel is damaged, so it makes it look like that cylinder's misfiring even when it's not. Could I have a sensor problem? you see where you got to get out of the box sometimes, and you will have cases where the code says cylinder one's misfiring, but I check cylinder one. Cylinder one ain't misfiring, but this code keeps coming back. And that's why it's important to ask the question, what makes the computer think it's misfiring? Another example would be a car that like Saab that uses ion detection. I have cylinder misfire codes. When I check the spark plugs, I find that someone put aftermarket spark plugs in with 4 ground electrodes instead of the single ground electrode. It uses ion detection. It has completely messed up the ion detection. It thinks everybody's misfiring. Car's not misfiring. Someone put the wrong spark plugs in it. And that makes sense because they're using the spark plugs for the ion detection. They put the wrong ones in. It'd be like using a meter with bad leads. So, you know, there's 2 things. That's why I always say a code is not a diagnosis. A code is a direction. And the 2 things to understand that direction is, first of all, what made the computer unhappy? What did the computer see to flow the logic to set the code? And what is the code telling us, and what possible causes could cause that code? So I want to look at both of those things, because many times it is as simple as, oh, a 301 misfire, I go check, I got a bad ignition coil or a bad spark plug or low compression or something. Yeah, there's something wrong with that cylinder. And that's going to fix the car probably on a misfire code 95% of the time, 98% of the time. But unless you can step back and ask the other questions, you're never going to fix that last couple of percent. And those are the cars where, hey, the code keeps coming back and I've replaced every part 3 times. Well, let's look at what's actually setting the code. I had something in chat and I lost my menu. There we go. A study group would have been helpful. So I should have assigned study groups, or you guys want to make a study group? Because you guys can always make a study group. The Zoom room is always available. You guys can always schedule a time to come into the Zoom room if some of you want to have a study group. And I thought I mentioned that the first week of class. If I didn't, I'll mention it again. So, I mean, you guys could certainly use the Zoom room and collaborate on that. If you guys want to have a Zoom meeting at 6 o'clock or whatever, I only use this room for classes, for ECC. I don't use it for other things normally. I'll set up different meetings. Like the class I taught on Saturday, I used a different room. So this is a resource for you guys. So yes, I do agree. Study groups are always helpful. It's just harder to do virtually. How many warm-up cycles will a B code stay in memory?
40.
40, correct. Because A codes, which are our fuel misfire codes, are 80, right? Because that's an A code. A code 1 trip 80, B code 2 trip 40. Kind of a quick way of remembering that. An A code will set for which of the following? Which of the following things would set an A code? Yes, number 4, ignition misfire. That's the only thing that's going to set an A code there.
Engine misfire.
The top 2 would set a B. The top one wouldn't normally not set a code, or could set a B code. Try that again. And there are some cars that if you pick up a misfire when you're out of gas, it's still an A code, but it'll kick on and say you had a misfire while you were running out of gas. So at least it lets the technician know that, yeah, you brought the car with a check engine light, and yeah, you are stupid. And we look at the tank and go, oh, it's full now. Okay, I think let me go drive the car. If it runs fine, it's probably already fixed. So diagnostic trouble codes, OBD1 versus OBD2. OBD2 requires code enabling criteria be met maybe twice before a code will illuminate. OBD1 only needed abnormality. So in other words, OBD1, as soon as you were out of specifications, we're turning the light on. When you're back in, we're turning the light off. OBD2 not only requires there to be an issue, but that issue has to happen under certain operating conditions. So every code has what's called enable criteria. Even the code for you leaving the mass airflow sensor disconnected, the enable criteria for it might be ignition has to be on, and it has to see that it's an open circuit for more than 14 seconds, and the voltage has to be above this level on the wire it's seeing that on, or below this level on the wire. So in other words, I'm seeing 0 volts on the power return wire, I'm seeing 5 volts on the return wire, but it actually goes into the enable criteria and says, look, this had to happen, this had to happen, and this had to happen. And when those things happen, we saw this for this long. And that's why we turned it on. So with looking at the enable criteria and looking at the vehicle, I can start developing tests for how I'm going to test is that happening. It also helps me decide what tool I need for a test. If it says, yeah, this happened and it happened for 100 milliseconds, I probably need a scope to see that. It happened for 14 seconds. I probably don't even need to get out a digital multimeter. I could use a scan tool if it supports a PID, because the scan tool is going to show me something happening for 14 seconds. Again, I can use this information to really help diagnose the vehicle. So for OBD2 emissions only, OBD2, OBD1 is not. So OBD2, remember, we're only allowed to turn that check engine light on if our federal test procedure is looking to be exceeded by 1.5 times. OBD1 was not. This is a little confusing how it's written, but most OEMs recommend fixing OBD1 first, opens and shorts, before checking and repairing OBD2. So what they're saying here is we always want to fix circuit codes before we fix logic codes. So a circuit code is a circuit is either high or low. Either it's grounded or it has voltage when it's not supposed to. A logic code is, I turned this on and it didn't work. The car's running lean. The car's running rich. We don't have enough flow through the EGR. We have too much flow through the EGR. My catalytic converter has low efficiency. Those are all performance codes. Those are logic codes. Opens or shorts codes are oxygen. It would be oxygen sensor circuit high, or ECT sensor circuit high, or TPS sensor circuit low. Those are circuit codes. And since if a circuit's not functioning correctly, that would certainly affect how not only a system works, but how it's evaluated. We always want to fix circuit codes first. OBD1, with few exceptions, was entirely circuit codes. It didn't have logic codes, with very few exceptions. So OBD2 is a lot about logic codes. So what it's saying is you always want to fix circuit codes first, logic code second. So if you have a circuit code and a low performance code, you fix the circuit code first and then retest for performance. And I still have this discussion in professional training, walking through case studies with experienced technicians. They want to go after the performance and not the circuit.
So Brian,
Yes.
cars can only be OBD1 or OBD2. Are they both the same, OBD1 and OBD2? So you
No,
can
they're
like,
very different. So
Yep.
OBD1 vehicles are California vehicles, light duty vehicles from 88 to 95.
Yeah.
Some exceptions, and then federal, and then heavy duty vehicles from 96 to 2006.
So how can it be like most OEMs recommend fixing OBD1 first before repairing
Got it.
OBD2?
Okay. That's what I was saying. This is confusing. What they're talking about here is OBD1, and I should really just rewrite this. OBD1 is opens and shorts. Okay, so that OBD1 logic is still inside OBD2.
Okay, that's what I was kind of like really confused. Thank you.
Yeah, so that OBD1 logic of those open and shorts, that circuit testing is still inside OBD2. So they're saying, hey, test the core pieces first before you test all the other stuff we put on top. It's a little confusing how it was written here, but that's what they're meaning.
Okay, that was what was confusing to me because I thought it was so different, and then here you're checking one before the other. I was like,
Right.
okay.
So we're really checking the functions of OBD1, which is what's called our comprehensive component monitor, is what sets those codes. And so we want to fix code set by the comprehensive component monitor before we fix code set by individual system monitors. So OBD1 versus OBD2 diagnosis. OBD1, the diagnostic procedure was to pull codes, record codes, erase codes, operate the vehicle, pull codes. And if the code didn't come back, it's an intermittent problem. Have a nice day. Thanks for the money. And then, of course, the light would come on the customer on the way home or the next day or 2 days ago. Later, the car comes back. We do the same procedure. Nothing to see here. Have a nice day. And eventually, the customer would get tired of coming back because we weren't really well equipped to fix it. The problems were intermittent. It wasn't failing long enough. And again, you can't check an electrical problem when everything's working. And yet, if you can't, so it was really a bad system. So what happened is customers completely lost confidence in the check engine light. Unfortunately, there's still XYZ auto parts stores trying to diagnose OBD2 vehicles this way, which creates a lot of issues. So erasing codes in OBD2 also erase my freeze frame data and all my monitor test results. So that's the last thing I want to do. And there was a real battle of this in the 90s when we were coming out with this new technology, and I was going to classes and coming back and going, hey, the guys in the shop are doing this wrong. And I mean, so there was a lot of issue. OBD2 has no what are called soft codes. So the two types of codes are soft codes and hard codes. Soft code is kind of an intermittent code. It's not always failing. A hard code is like a wire shorted together. It's shorted. It's not going anywhere. It is bad all the time. Soft code would be a wire touches sometimes. In OBD2, we don't have soft codes because of that two-trip detection. We're not going to fail every time that thing touches for a second. Where OBD1, man, if that thing was out of parameters for a second, it would turn the light on. OBD2 says, no, we want 14 seconds on some cases. We want to see it happen twice. So now there is enough consistency that it should be diagnosable. OBD2 diagnostic procedure is pull codes, both current and pending, record freeze frame data, inspect monitor test results, repair the root cause of the failure, operate the vehicle at the freeze frame data parameters, meet the code enable criteria, run the monitor, and verify the repair. That's a lot different, isn't it? So we're going through and using the data to verify that the system works. If you notice, we're not clearing stuff until either we're ready to run the monitor at the end, or we might not clear it at all and just run the monitor and see if it passes, depending on the code, and then clear everything to give it back to the customer. So very, very different procedure. So which of the following is the biggest advantage of the OBD2 system?
I am confused between 1 and 2.
I couldn't quite hear your answer. Okay. Yeah, I see.
I'm choosing between
I
1
say
and
1.
2. 1 and
1
2.
turns on the mill as soon as the fault is detected. Well, OBD2 doesn't do that. OBD1 did that. That was one of the problems with OBD1. Vivian sent me the correct answer in the text. Number 2, it detects deteriorated components. Remember, OBD1 was either it's completely broken
Should be
or it's
3.
okay. OBD2 detects things as they fail. So once they get below a certain performance level, it'll now be able to set a code. So for example, we use the example of a misfire. When it sets a misfire code, it's not misfiring every time. It's misfiring over the percentage of time that is allowed to misfire. So depending on the generation of the vehicle, depending on the code, that might be 33.4%, it might be 24.9%, or it might be 0.99%. But if it is misfiring over that threshold, that's what sets the misfire code. We're not waiting until it misfires every time. We're waiting to when it misfires enough that performance is deteriorating. Remember, we want to set that code and turn that light on anytime we think we're going to get 1.5 times the federal test procedure. Not 2 times, not 5 times, not 10 times, not 1,000 times. It's as soon as we hear it, right? As soon as we've deteriorated enough to hit that 1.5 times. So this is a key point, and I'm sorry if I didn't emphasize it more earlier. And that's one reason why I put the question in here to hold my feet to the fire. Is that the biggest advantage of OBD II is that we are detecting deteriorated components and systems. We're detecting things as they deteriorate. I mentioned the catalytic converter. Most manufacturers set a code for a catalytic converter at about 50% efficiency. It's not dead. It hasn't stopped working. Matter of fact, the car is still probably running clean out the tailpipe as long as the engine's running good. But if the engine starts running bad or has a problem, there's no longer enough capacity in the catalytic converter to keep the vehicle clean. So therefore, we're going to set a code for it because it might pollute, not that it is polluting. So we really hedge that, right? It's deteriorated.
Oh, Sir Brian, number 2 detects deteriorated components is the biggest advantage, but number 1 is also an advantage, right? It's just number 2 is the biggest.
Yeah, number 1 is not an advantage because number 1 doesn't apply to OBD II. That would be OBD I. OBD I
Okay.
turned the light on as soon as it detected a fault.
Okay.
OBD II doesn't do that. OBD II, what, takes 2 trips of seeing the fault many times before it'll turn the light on.
कोई मॉडर्न के लिए आता है मॉडर्न बहाने सब गिरा हुआ है।
So code enable criteria. So we have a couple of different kinds of criteria we're going to talk about in this PowerPoint. One is code enable criteria. The other is monitor enable criteria. So certain codes will only set during a monitor. But right now we're going to look at code enable criteria. So the definition is once the conditions are met to test for the DTC are met, then the monitor will run the test. So poor English, and I didn't write it. So once conditions are met to perform a specific test to evaluate whatever it is we're testing. So for example, I mentioned misfire. Misfire breaks the engine revolutions into blocks of 200 revolutions, or 200 cycles actually. I think is it revolution or cycles? Maybe it is revolutions. But blocks of 200. And what we're looking at is, did you misfire too many times within that 200? Or when I put 5 of these together at 1,000, did you misfire too many times within that 1,000? So in order to set a misfire code, I need to misfire a certain percentage of time within that 200 revolution block or 1,000 revolution block. If I don't misfire enough times, it doesn't set a code because I haven't met the enable criteria. That being said, if my car's running out of gas, we may disable that. And now we're not going to test for misfires because we know you are running out of gas. If you have a 4-wheel drive and put the car in 4-wheel drive low, it may disable that because it knows in 4-wheel drive low, and we're trying to look at crankshaft rotation, it's going to get jarred if you're off-road and you're in your low speed. So I really can't trust that because my crankshaft is no longer just affected by the engine cycle, but also affected by what the drive line's doing. So I might disable that. So I might see part of the enable criteria is you can't be in four-wheel drive. You need over 15% gasoline. You need, so we have a list of things that have to be met. P0134 O2 sensor, bank one sensor one remains its center code. Conditions from one manufacturer. Runtime over 2 minutes. ECT sensor input more than 176 degrees Fahrenheit. Then the test started and the PCM detected that the front O2 sensor signal was at 0.5 volts fixed for 1 minute or longer. So this is not, gee, we had a little glitch. This is not something hiccuped. This is, the car's been running for more than 2 minutes. The engine is above 176 degrees. And after those things are met for 1 minute, the sensor didn't move from 0.5 volts. That's a dead sensor. So I really don't need a lab scope to see this necessarily because it's happening for a minute. I can use my scan tool and look at the voltage on the scan tool. Gee, it's not moving. I just duplicated. Now I might need to use a meter or a scope to verify that, verify wiring. Many times with sensors like this, we're going to do a visual inspection of the wiring. We have two sensors. I have a front sensor and a back sensor. If my back sensor is reading rich and lean and my front sensor is not doing anything and all the wires are hooked up, it's getting a sensor. We're not even going to go down the rabbit hole looking for some weird problem until we put a sensor in it. It just doesn't make sense. You'd be spending hours testing something that 99.9 times is a sensor. But that's also why you always, I'm going to put a new sensor in it and retest for proper operation. Now I get the same result with the new sensor. Now we know we got something weird going on. Bad PCM, something weird in the wire, something weird. Now we got to get to the PCM that might not be easily accessible, get to the wiring. I got to check signals at both ends. Now I'm using a couple channels of a scope. I mean, that's another hour or two diagnosis. Why would you charge every customer that extra hour or two diagnosis to be thorough? You're not. You're going to go with, this is what it most likely is. I can see by the data it's telling me that. Let's put that in. I'm doing a quick visual inspection, make sure no wires are damaged. Because where are wires going to be damaged normally? Inside the car, under the car where the sensor is. So that's where you're going to do your visual inspection. But that's an example of one code enable criteria. So every code has enable criteria. And that code can only set when that enable criteria is met. So for example, this sensor could stick for 50 seconds and start working again. And then stick for 40 seconds and then start working again. And stick for 55 seconds and then start working again and continue to do this. You would never get a code, but you'd have a car that didn't run right. Because you didn't met the code enable criteria. It's not that there's not a problem. Is that the problem wasn't bad enough to get over the manufacturer's threshold for setting the code. It didn't meet the enable criteria. And that's why not only is a code not a diagnosis, but why I also say just because the check engine light's on or just because there's no codes doesn't mean there's no problems.
And these thresholds, Sir Brian, these are set by the manufacturer and in the system already. So if
Yes.
these are not met, that's when this code alert will come out, right?
Exactly. So this is completely set by each individual manufacturer for each code. So I could have the same code number and one manufacturer may set this after 2 minutes. Another one may set it after 15 seconds, right? I mean, so, you know, and one manufacturer may say, hey, it was stuck at 5.5 volts. Another manufacturer may say it's stuck at 450 millivolts. Or another manufacturer, which is common for this code, says it didn't go below 300 and it didn't go above 600, which means it didn't see lean, it didn't see rich. but I could still have what? A fair amount of movement there where it might look kind of okay, but now I need to go in and actually look at what voltage thresholds it's crossing. So, you know, the voltage could change, the time could change. The one thing that's consistent about a P0134 code is it's for the bank 1 front oxygen sensor, and it's saying that it's not switching. So here we see the word remains at center. Another manufacturer may just say not switching. Right? So you get into the terminology a little bit there. And that's why I said, if we have a code, we need to do research. We need to look at what did the computer see? That's the enable criteria. This is what the computer saw to turn on the light and set the code. It saw the sensor with the engine warm after being run for 2 minutes, see the oxygen sensor not move for more than a minute. And it was not moving, stuck at 0.5 volt or close to it. That's what it saw. So before I go test the oxygen sensor, before I go look at the scan tool data, I want to do this first, because otherwise I'm just looking at data going, gee, it looks okay, or it does look okay. I really don't know, because I don't know what is making the computer unhappy. And again,
is this information usually included in the scan tool?
No.
You got to look it up somewhere else.
Gotta look it up somewhere else.
Yeah.
Now,
that's my
some
question
scan
also.
tools like Snap-on have a troubleshooter function where they will give you some of this information for some codes. So that saves you another trip, which is a real nice. Other scan tools don't have that. Some factory scan tools not only have it, but walk you through the whole diagnostic procedure. But those tend to be some very high-end European scan tools for European vehicles. So consequently, I'm going to all data and looking this up. And so when we look at our level 1 diagnostics, part of that level 1 diagnostics is not only getting information from the vehicle, but also getting information about the code, right? Is doing research. What did the computer see that made it unhappy? What, you know, is there a pattern failure for this? In other words, I have a code that might be a little more complicated, maybe a system code that involves 3 or 4 different expensive pieces that are hard to test. So I might do some research and find, you know, is this code common for this car? What normally fixes this code? So that way I can spend my diagnostic time going and testing the component that fails the most often, right? I mean, why test everything if, hey, 800 people say this part fixes it. Okay, let me go test that part, since that seems to be the one that's going bad and the dealer has 10 on the shelf. I'm thinking that there's a high likelihood here. So we use it for setting priority of diagnostic testing, also helping us with diagnostic testing. So this is a huge thing. And unfortunately, this is a step that many technicians skip. I don't want to take the time to go look up that stuff. It takes too much time. Well, how much time are you going to waste fumbling around in the dark? You know, this code enable criteria a lot of time tells me not only which tools do I need to diagnose it, but how much time I need to spend diagnosing it. You know, what if I hook up to the car and the oxygen sensor looks normal? All right, well, we know this thing is dropping out, and we know it's dropping out warm. So maybe I need to go park the car and let it run for 20 minutes and then come back and test the O2 sensor. Maybe it drops out after it's been running a while. You know, maybe there's an intermittent wiring problem, and that's why it's working fine now, because 1 minute is not an electrical connection doing a quick touch. 1 minute is something happened. I should be able to see that. And not only that, but it had to happen what? Twice. 2 consecutive trips, or at least 2 trips, not necessarily consecutive, but under similar parameters. But it had to happen twice for over a minute each time. I should be able to duplicate that. So if it looks normal now, I shouldn't be giving it back to the customer. I should be, okay, let's let it run some more, because I know it doesn't do it right after I start. I mean, it might be slow warming up or something, but we got heat. So my next question is, because we have a monitor for testing the oxygen sensor heater, was the heater tested? If the heater was tested and passed, it should be coming active on time. If the heater wasn't tested, or I don't know if it was tested because someone cleared all the data, now it might have just not been warming up, and I might have a bad heater, but I don't have a code for the heater because someone already cleared that. and now it can't test it. So you see where when someone clears data prematurely, you have a lot more possibilities on what might be wrong. If I have good data, now I can use some good data, and I can figure out, a good test strategy to try to duplicate it. And so tomorrow we're going to look at our 1 and 2 trip DTCs. We're going to look at freeze frame. I'm going to talk a little bit more about what freeze frame actually is and how we use it. And that's huge, because that's what I would be using here to figure out, really how to duplicate the situation. And newer cars have more freeze frame data than older cars do, but there's still only 8 things that manufacturers are required by law to give us in freeze frame. So I know I'm always going to get those 8. If I get 30 or 40, that's great. More is always better. But we'll break down how to leverage those 8 things, because they're not always what we want, but that's what we get. So we need to be able to use that to understand what's going on with the vehicle. So hopefully I cleared up a couple questions people have had on OBD2, or things they've had with their own car about why did this happen? Why did it take 2 weeks to come back? And I know Cynthia, I made her head explode, and she's more confused than she was at 7:30.
You're right, sir. One question, sir. This enabling criteria, are these available readily to the technician so they can identify what cost of code, so like a reference, so for easy diagnosis? Is this with a user manual or?
Yeah, today most of the time they are. I was just looking for one of my books. I cleaned up I had to doing some remodeling at the house in my office, and I think I put the book away and I don't have it out.
Because you said it's very helpful in determining the code, what sets the code. So they should have the criteria available.
Exactly. So for example, right. So for example, all data has that in it most of the time, which is why I like all data. Mitchell traditionally does not. Mitchell takes you straight, doesn't tell you what set the code. It just takes you to a chart to follow to try to figure out what's wrong. All data tells you what set the code and shows you the chart. So that's why I like that. And hasn't always been like that. Back in the late 90s, early 2000s, that information was not available. And I actually bought books. They were about this thick, and they were, a small book for about $100 each. And I bought like 8 or 9 of them for different manufacturers just to get this information, because that was so important to get, and it was not available. And so, buying a set of books, I was spending $800-900 on a set of books just to get this information as a technician, because this is what you needed to fix cars, and it wasn't anywhere else. There was a company that had taken the time to compile the data from OEs, from manufacturers, written these books, and they were very expensive. But boy, they bridged the gap until the major information provider like AllData started supporting that information. And now those books are obsolete, basically, because that information is a bit more widely available.
Okay, that makes sense. Thank you, sir.
You bet. Well, everybody, have a great rest of your day. Don't forget to participate in the discussion forum that's going on today. I think it's due tonight. And I will see everyone in the morning.